Now, in 1924, Sir Arthur Eddington established a very important relation between the luminosity and mass, but only for main sequence stars. This relation does not apply to red giants or white dwarf. Basically, what he found for main sequence stars, he measured the masses of main sequence stars, as we discussed, by looking at the binary star systems and applying the third Kepler's law as formulated by Newton. And he found that for all main sequence stars, luminosity is given essentially in, there is some constant, but it's proportional to the mass of the star to the power 3.5. Okay? What that means that as we go down the main sequence from very luminous stars to those that are more dim, the mass of the star decreases. So as you go down the main sequence, the luminosity drops, and so does the mass, but not in an arbitrary way. The two are precisely related like so. So the more massive star is, the higher the luminosity, and vice versa. Now, with this relation, we can then actually get an estimate for the lifetime of a main sequence star. As I've discussed before, lifetime is basically given by the fuel available of a star, and is inversely proportional to the energy output of the star, right? Just like with a car, you can drive longer if you have bigger tank and you don't speed, you don't burn the gasoline at high rate, right? Then you can cover longest distance. The same is here, right? The more material there is in the star to be used as a fuel to fuel its energy production, the longer it's going to live, but the lifetime is inversely proportional to the energy output of the star. The more energy it emits for a given amount of fuel, the shorter it's going to live. So the fuel available is basically given by the mass of the star. And energy output is given by the luminosity, right? How much energy it produces per unit time. But Eddington found that luminosity is basically given within a constant as mass to the power 3/2. So then we get that the lifetime is determined by mass as so. That is, it is inversely proportional to the mass raised to the power 2.5. So the larger the mass of the star, the shorter the lifetime. That means that those stars at the top of the main sequence, those that are very luminous and very hot, they don't live very long. Okay? That also implies that we cannot see massive stars that often, because those don't live very long, and the odds are that they have burned out before our lifetime. Astronomers do see some stars with masses over, say, 30 solar masses, 50, even 100, but they are not very common, simply because they don't last very long. So this then tells us the stars at the top of the main sequence, and they are luminous and hot, therefore blue, have short lifetimes. At the same time, the stars at the lower right corner of the main sequence, those with low luminosity, they also have very small mass according to mass-luminosity relation. And according to our estimate for the lifetime of the main sequence star, they are going to live long, the longest. These stars are often referred to as red dwarfs. Red because they have low surface temperature and appear to be reddish, but because they have low luminosity, it means that they also have small radii, and therefore they are small in size, hence dwarfs. And it is estimated that their lifetime is going to be longer than the current age of the universe, which is about 13.7 billion years, right? They got formed at some point, and those of you who signed up for Astronomy 1 PO2 will learn about the star formation, our current understanding as to how the stars form. And they got formed at some point, but because they have a relatively small mass, they burn energy at low rate, and as a result, they are going to live for a very, very long period of time.